A 2 centimeter by 3 centimeter rectangle lies in the xy plane. Find the electric flux through the rectangle if, part A, the electric field has x component of 50 newtons per coulomb and a y component of 100 newtons per coulomb, and part B, the x component of the electric field is 50 newtons per coulomb and the z component is 100 newtons per coulomb. Let's begin by sketching a picture of an XYZ coordinate system. We will have the y-axis vertical, the x-axis horizontal, and the z-axis is coming right at us. The units of each of these axes will be in centimeters. Let's also indicate a convenient scale. This will be 1 centimeter, 2 centimeters, 3 centimeters along the x-axis, 1 centimeter, 2 centimeters, 3 centimeters along the y-axis, and 1 centimeter, 2 centimeters, 3 centimeters along the z-axis. The rectangle is 2 centimeters wide and 3 centimeters high. The area vector is perpendicular to the rectangle, and for this problem, let's draw the area vector parallel to the z-axis. Since the area vector is parallel to the z-axis, its normal component will be k hat. We will define A to be the product of 2 centimeters and 3 centimeters. Therefore, the value of the area is 6 centimeters. Let's indicate that this area is perpendicular to the Now that we have the area vector and the area drawn, let's add an electric field vector, at least one electric field vector to this sketch. The electric field has components of 50 newtons per coulomb in the x direction and 100 newtons per coulomb in the y direction for part A. Let's indicate those components like this. We have, I am going to say the electric field is E naught I hat plus 2E naught J hat, where I am defining E naught to be equal to 50 newtons per coulomb. So notice this means that the x component of the electric field is 50 newtons per coulomb, and the y component is twice that at 100 newtons per coulomb. Let's indicate this in our picture. Since the y component has twice the magnitude of the x component, and since the electric field lies in the xy plane, I am going to just simply draw my electric field vector from the area vector. So I'm going to come over basically 1 unit along the x, go up 2 units along the y, and that 2 units along the y would put us up here more. So that's going off my rectangle, but that doesn't really matter because this is just a sketch of our electric field, and the scale for the electric field doesn't necessarily match the scale for the coordinate system. I'm just using the divisions in this coordinate system so that I could at least scale the x component of the electric field and the y component of the electric field proportional to each other. So here's the electric field. At least it's the electric field at the point at which I drew it, where I located the area vector. Since the electric field is in the xy plane, and since the area vector is perpendicular to the xy plane, that means the area vector is also perpendicular to the electric field. Because the electric field vector is in the xy plane, it does not cross the plane. Therefore, I know conceptually the flux should be 0, because we only have electric flux if electric field lines cross the plane of a surface. Here it doesn't. Let's illustrate that by taking a top-down view of our coordinate system. Let's look down from the positive y-axis. As we look down from the positive y-axis, the z-axis will be going straight down, and that doesn't look straight down to me, so let's try it again. The z-axis will be straight down, and the x-axis is going horizontal and to the right. I will indicate my units. This is 1 centimeter, 2 centimeters, and 3 centimeters is before. And along the z-axis, I'll just do 1, 2, and 3 as well. These are all in centimeters. Let's add our rectangle, which is positioned in the xy plane. Our rectangle is 2 units wide in the xy plane. Let's add our area vector. Our area vector is in the positive z direction. So from this vantage point, our area vector is going down. Now this scaling isn't necessarily corresponding to the rectangular coordinate system scaling. So I'm just drawing this area vector, some arbitrary length, primarily to indicate that it's perpendicular to our rectangle. And this area vector again is given by a k hat. Now looking down on this, remember that electric field vector we drew in the previous page? Let's look at that again. The electric field vector is in the plane of the rectangle. So E is in the xy plane. We know this because it only has an xy component. The components are constant, so the E field is constant. So really there's an infinite number of E fields in this xy plane, and I only started off with drawing 1. But if we were to try and draw a more complete picture of the E field, being a uniform field, that E field probably looks something similar to this. It's a uniform field. There's a number of field lines there. Well, when we look at that uniform field in the sketch on the next page, none of the field lines actually cross our surface. The electric field only has a x and a y component, no z component. With that said, we could see that the area vector is perpendicular to the electric field vector at any point on that surface. Since no electric field vectors is crossing the surface, we could say that the electric flux is 0. Now, technically, from this vantage point, the electric field is a uniform field, and it's true for any value of z. So from this top-down approach, the electric field would probably look something like this. We lose the perspective, however, of its orientation in the xy plane. We lose the x component and the y component, which we know is angled upward, as we can see from this diagram. The important thing about this diagram, though, is we see that the electric field does not cross the surface described by this rectangle. Because no electric field lines cross the rectangle, we know that the electric flux should be 0. Well, let's derive that. Let's use our formula for electric flux to calculate what it should be in this circumstance. We have that the electric flux through a surface is given by the surface integral of an electric field through that surface. The electric field has constant x component and a constant y component. The area vector is in the z direction. So if we take a tiny bit of area, that tiny bit of area will also be in the z direction. Let's take the dot product of the two. The dot product of the electric field and the area vector is going to be given by, and we could do this a couple of ways. The first way, I'll write it like this. This will be given by the sum of the products of the components of the electric field and the area vector. So this would be the x component of the electric field times the x component of the area vector plus the y component of the electric field times the y component of the area vector. Notice this is just 0. Therefore, the electric flux through the surface for this first situation is equal to 0. Well, let's look at this. Let's evaluate the dot product alternatively using the cosine. We have the dot product between the electric field and the area vector is going to be equal to the magnitude of the electric field times the magnitude of the area differential times the cosine of the angle between the electric field and the area vector. We know that the angle between the electric field and the area vector is 90 degrees. Because the angle is 90 degrees, we know that the cosine of 90 degrees is equal to 0. Therefore, that product of the electric field and the area differential is equal to 0. Which means that the electric flux of the electric field for part A that lies only in the xy plane and the area of the rectangle that lies only in the xy plane provides an electric flux of equal to 0. So we had two ways in which we calculated this using calculus. Two ways in which we applied the dot product. The first way in which we applied the dot product was by looking at the components. The second way we applied the dot product was by looking at the orientation of the electric field and the area vector. However, conceptually, we knew that the total flux must be 0 because no field lines crossed the plane of the rectangle.